Pleasure, immense pleasure to introduce Steve Smale this morning. He has been very influential to the development of IMPA, as we explained the other day, the central figure. Today, he's going to speak on perspectives on the Pitchfork Bifurcation. This is Steve.
Thanks, Jacko.
You don't need that.
I guess not. It's okay? You hear me?
Okay.
Okay, so let me start today by giving some references. So there are 3 papers: math of the genome. Second one is the pitchfork. And the third one is the emergence of function. And the fourth one is not written, and that is the math of the cell cycle. So these 3 are all of them in collaboration with Indika Rajapaksa. His name is easy to remember because it's the same name as the head of Sri Lanka, at least for a long time. So this is Indika, and they're all on archive. Actually, this one is accepted and is published online by the Journal of FOCM. So this is the background of what I'm speaking of. And right today, I'll talk mostly about the pitchfork, or at least the first half. Okay, so the pitchfork bifurcation, let me remind you, is of this form. It's a 1-parameter family of dynamical systems defined by F mu, for mu real, equals mu x minus x cubed, 1 variable. This is quite classic. Okay, so this is the normal form and the basic aspect of the 1 variable pitchfork. We can look at this, and we want to look at the equilibria. Let's see, I guess this is right. So this is going to be 0 at, equals 0 if x equals 0. I should write here f prime, I think. The derivative with respect to x, or x squared equals square root of mu. Okay, so what? Plus or minus, right. Very good. So we can look at it this way. So for mu positive, let's just take mu positive. So it's going to come something like this, 0 being an equilibria, and we have these 2 other equilibria. So the basic idea of the pitchfork, it converts for mu less than 0, a stable equilibria, into 2 stable equilibria with a saddle in between. I think many of you have seen this already. It's in a lot of textbooks and so on. Is that right?
It's not the shadow, it's the source in one dimension.
It's the source in one dimension. Yes, you're absolutely right. Right. Okay, so what I'd like to do today is develop this theme, try to convince you that this is correct, but is wrong. So mathematics can be correct and still wrong if it gives rise to the wrong concepts. And my claim is that this is wrong. And this is the basis for all the literature on the pitchfork. So I will really work hard to convince you that this gives a wrong picture. And here's a rough reason. This is missing a second derivative term. Okay, so then people say it's codimension 1. The phenomenon is codimension 1. And they say that this is not robust because of a second. You can always add a small second derivative. So that's the lessons people have drawn from this picture, that it's not robust, and it has this question about no second derivative. Okay, so in the first paper in that list, Mike Schub was the editor, and he wrote to me, I wrote him at one point, it said, "It sounds to me like you don't believe in the pitchfork." And he wrote back, he was the editor, he said, "Yes, and my referees, 3 referees, also don't believe in the pitchfork." So I said, we could check Google under pitchfork, and there would be 100 references or more to physicists using it frequently. So we had a long, tough correspondence on this issue. Eventually, he helped me solidify our work on the pitchfork. So he played a good contribution by his challenges, claiming all the time that this is codimension 1, therefore you won't see it in physics or biology. So this challenged me a lot to make sense of the pitchfork. And we did, in the first paper, some of that, not completely. But I found, or we found, subsequently an example which gives complete clarification of everything I say I believe. And so this is what I'm asking you to look at, and I'm trying to convince you it makes sense what I've just said. Essentially all the literature on the pitchfork gives the wrong impression. Some of the best work is done. Most people just leave it at one variable. Some people extend it to many variables, and they have as a hypothesis conditions which force the second derivative to be 0. So you always have this so-called codimension 1 phenomena, which I think is wrong. But remember now, the pitchfork has this property of converting as a bifurcation parameter changes. It changes from a single stable equilibria to 2 stable equilibria. So that's the characterizing feature of the pitchfork, going from 1 equilibria to 2 stable equilibria. And I'm talking stable equilibria. Stable equilibria play the biggest role imaginable in applied math. They're the ones one actually sees in physics or biology. So that's why I want to focus on the pitchfork and the stable equilibria. Okay, so let me go ahead and give another example. So this is a normal form, and one can start in the one variable case with some kind of hypotheses and derive this. And you'll see that in our first paper. Okay, and that was partway to this result. But now let's look at another example. X prime equals y squared. This is going to be in 2 variables. going to be symmetric for the moment. Okay, so this is a differential equation in the plane in two variables. Okay, and this is symmetric, and so this doesn't, some people make a symmetric hypothesis to get rid of the second derivative. This has got the advantage I can change this A to a B to make it non-symmetric. Doesn't change anything much. Okay, in our second paper here on the Pitchfork, what we do is we have found some great software which shows this in a way that you can just vary the parameters A or A and B and just follow the whole development of the dynamics very, very well. You can find that link in our second paper. I was going to put that on a slide and show you the link in person, but I didn't. So I'm just going to describe in words and some pictures what's happening. Okay, so I want to analyze this. And my belief is that it has not been done before. A is our mu. A is the bifurcation parameter. Okay, so we want to look at what's happening in the dynamics as A changes from negative through 0 through 1. Okay, so here's some pictures. You see, this is all just parabolas. Everything is parabolas. So what we're doing now is looking at a geometry of parabolas, which has got a lot of appeal to it. Everything can be seen in terms of parabolas with one or two parameters. Okay, so let's look at what are called isoclines. So we want to look at x prime equation equals 0. These are called isoclines sometimes. Then y prime equals 0, same. So we have two isoclines. When they intersect, we will get the equilibria. So these isoclines are parabolas. It's all very simple pre-calculus mathematics, if you want. Okay, so let's look at, say, x and y. If a equals 0, we get the basic parabola. I think it's going to look something like this. This is going to be the equation for x prime equals 0. You can correct me if you think I make a mistake or if I do make a mistake. Okay, so that's the first isocline. This is the parameter a equals 0. The second isocline then would then be like this, another parabola for y prime equals 0. Okay, and you can see it read right off from this. If we take for a equals 0, then they intersect, something like this. Intersection of two parabolas. It will have two equilibria. And this is extraneous to our discussion. So we're only concerned with this equilibria at 0, at the origin of the plane. All right, so this is at the parameter value a equals 0 for both. And here I've superimposed them, so the equilibria will be the intersections. Okay, now I want to change it to a. If a equals 1, then we'll get a tangency. So we can see from here, if a equals 1, the two derivatives are tangent at the curve. Okay, so for a equals 1, you have a tangency at 0, and that's going to be the bifurcation point. So a equals 1 is the bifurcation point. Remember, a is our bifurcation parameter. So a equals 1 will be when the these isoclines are both 0. And so that's going to be this origin. Okay, now we're looking at, let's take directly A. For blackboard space, I'm going to take A bigger than 1. So then the first one for A bigger than 1 is going to look like, and this gets a little tricky, like this. This is x prime equals 0. These are all just parabolas, but as A changes, this parabola is being translated, so the this endpoint is going to be moving from the origin over here. So this is the isocline typically for A bigger than 1. Okay? So now I want to look at the same thing for the y prime equals 0 for A equals 1. That's going to have a picture, if I'm not mistaken, something like this maybe. And now this is, just even though I'm working with two parabolas, it's a little tricky to get this diagram straight. So let's see, it's going to be coming down something like, is that right? This would be y prime equals 0 for A bigger than 1. And so we see our equilibria here. Here's the extraneous one, which we don't care about. Here is the old equilibria, which has become a source. And here are the two new equilibria, which are the two basins. And one can check either using analytic geometry or some kind of calculus. You can check what I've just said, that we get two sinks, two basins, these side, and this is the original equilibria, which has become a source. There's a saddle. It's a saddle. It really is a saddle now. And so you have a stable manifold coming up, something like this. This would be WS of 0. And then we have everything over here converging here, here. So this is the separating. Does this seem to be making sense? Okay, so what we have here is our model for the pitchfork in 2 or more dimensions. This is, I claim, a good model for the pitchfork, a good normal form. This is the normal form, and you can get away from symmetry just by putting B here, and it doesn't change the character. So if this is making sense, I'm most of the way there, because we have something now robust. If you perturb this, it still has the same character. This is a robust model and contradicts just about everything you read in the literature about the pitchfork. The third derivative is 0 from the beginning. There is no third derivative. So we don't need a third derivative hypothesis when we go from one variable to more than one variable. This same model works for n variables. We could just take the last n minus 2 variables, something orthogonal here, and contracting. Nobody challenges me on that.
Question, does it mean that all the terms that you keep here are resonant?
Or what?
Does it mean that all the terms that you are keeping here are resonant? Or can you get rid of them by change of variables?
Resonant. I'm not sure what resonance would mean in this context. There's no periodic solutions at all anywhere near any of these.
But I mean, you cannot. Terms which cannot be eliminated by change of variable.
Yeah, I'm not sure about that. For the one variable case, it's very complicated. So we deal with that in the first paper, I think in a good way, but we didn't appreciate this example in the first paper. And so the main thing for me is the robustness of these equations. They're robust. If you change any a's or anything here, you get the same picture.
So, Steve, the critical point at the origin initially is degenerate.
At the bifurcation, of course. Before the bifurcation, no.
So you're taking a degenerate critical point, and you have a slice in the parameter space and seeing where it bifurcates.
Yeah.
So if you keep the quadratic nature of this, of course, it's persistent.
Right.
If you look at general perturbation,
Oh, I think if you take general small perturbations, see, this has got this kind of stability to it. If you had any perturbations which are small, you keep this picture. You have to say what it means to be small relative to the parameter. Yeah, of course there's a parameter. At the parameter value, a equals 1. I haven't written that. Oh, it's here. Yeah, of course that's degenerate. That's the bifurcation parameter. Before that, before mu equals 1, then you have the stable picture as we've described here. So this is stable for mu less than 1. At mu equals 1, you have the parameter becoming a critical bifurcation parameter. So of course, at that point, you have to be careful what you mean by robust. Well, you can do that. But you see, especially if we take bigger than the bifurcation parameter, we have this highly stable situation for any a bigger than 1 in which any C infinity small perturbation will leave the same structure. I hope that helps. I don't know.
I have a challenge.
What's that?
I have a challenge. So if you take the direct equations, which is a three-dimensional ODE, it has no cubic terms. It has a Pitchfork bifurcation.
The three-dimensional. Yeah.
This is kind of, so this is known that you don't need odd terms to have Pitchfork bifurcations.
What is known?
It's known that you can have higher dimensional differential equations with just linear and quadratic terms that have Pitchfork bifurcations. Yeah, but if you make change of variables to the resonant term, then the cubic term appear. Yeah, but the comment was that this equation had no cubic terms, and therefore this was a conventional wisdom by saying that's even known.
Yeah, well, I am especially impressed by the referees in bifurcation theory, which Mike Schub chose. And they said what I was doing was all wrong because it contradicted well-known facts in bifurcation theory. Mike himself took a long time to convince that we have something which is a codimension 0 bifurcation in the language of bifurcation theory. And it doesn't need any third-order terms. Of course, if you add on any perturbations to it, if we take a bigger than 1, now we can add on any perturbations, even C infinity, which are small enough, we'll keep the same picture. Anyway, that's my view of this. And what's key here is a condition we found in the first paper. And the problem is, it was it's confusing to the referees and Mike and to us too, is the difference between a saddle node and a bifurcation, Pitchfork bifurcation. There are two things which look alike, saddle node bifurcation, just in one variable, and a Pitchfork bifurcation. For example, a saddle node, here we have one variable graph. Then as we get here, we could have something happening like this. We can have approximations like this, which converge to this picture, and it's a saddle node. And so one has to deal with the question of avoiding a saddle node. And it looks from this picture like obtaining this, which is more like the Pitchfork, that is something wrong. So what one has to do is to build in the hypothesis which will allow us to obtain this equation or this equation. And here's the hypothesis. This is a hypothesis which I'm pretty sure is new, and that is if we're looking at f mu of x, this can be any variables. Say mu equals 0 is bifurcation. And suppose now the determinant of f mu at 0 equals 0, and we have a single eigenvalue crossing through 0. So we look at lambda 1, say, equals 0 at 0. So this is a setting which could be both a saddle node and a pitchfork, two different things. So what we do in even our first paper is hypothesize the following, that we look at the dynamics of f at the bifurcation point, f at mu equals 0. So we look at this at the, say, the bifurcation point 0. So this is going to be a dynamics in n-dimensional space. And what we demand is that this is a sink. But it can't be a real sink because of this condition. So this is a, quote, sink, topological sink. So it means even at the bifurcation parameter, there is some neighborhood of 0 which is contracted to 0, not so uniformly, but is contracted to 0 under the dynamics. It's a basin in a topological sense. So we have to make this hypothesis. We do make this even for one variable to get away from this picture here of the saddle node. To exclude the saddle node, we have to say the bifurcation does not allow the equilibria to escape the basin. Another way of saying it. So with this hypothesis, even before we had this example, we had a result to deriving this in some more general context. But we didn't realize we didn't need the third derivative to be 0. We didn't realize that. Because one can look at this without thinking of this, and you still were giving the wrong impression. Yes?
So just one comment. If you look at your differential equation, it's invariant under symmetry. That situation, you have this kind of system. If you just interchange x with y, you have the same equation. So when you flip it, line y equals x, that's preserved. Same thing as e instead of not the rest.
Right.
There, this is a known stable bifurcation.
Sure. But I can just put b here. And let b equals a squared or some function of a. You get away from the symmetry.
At some point, but after you've gotten to a stable situation, right? I mean, when you do this around a b equals 0, what happens?
Same analysis. Oh yeah, if you take a and b, very generally, you get same picture.
That does not mean that there is not another system of variable where you have a symmetry. I mean, usually when you have a pitchfork bifurcation, this means that you have some symmetry. If your symmetry is broken, the pitchfork will degenerate into a saddle node and a continuation of a point.
Yeah.
This has been looked at.
That's a conventional theory, which I say gives the wrong picture.
But that's what you see when you do a numerical experiment.
Oh yeah, if you don't assume this condition, on the bifurcation does not allow the bifurcation point to leave the basin. You have a uniform sink, strict sink for mu less than 0, and the sink has remained topologically even for mu equals 0. See, that will exclude the saddle node in any dimension. This works in any dimension. So this is the hypothesis we're making to establish the bifurcation even in this case. If we take n equals 1 now with that condition, then one can establish this. Okay, any more questions?
Yeah, you're also assuming, we're not just assuming that trajectories stay in the basin, you're also assuming that there exists a trivial solution. So actually a Pitchfork bifurcation is not codimension 1, it's codimension 2. So you're getting two conditions. Why it becomes
Well, you could look at it that way. I prefer just to say what we mean by a bifurcation is bifurcation where we have this determinant vanishing, multiplicity 1, and this condition.
Do you mean that in the space of all dynamical systems and in dimension 2, the Pitchfork is a generic bifurcation?
I didn't prove that, I must say. But yeah. This, if you assume this condition, you have to always have some condition for a bifurcation. And this is our condition. And a non-degeneracy for higher derivatives and so on. So you assume some non-degeneracy condition, but this is the main condition. And then, yeah.
Yeah, but you, for instance, very often people assume that there is a symmetry because the symmetry is, there are two types of symmetry in physics, the one which comes from apparatus and the one which comes really from the structure of what you look at. And you cannot break those symmetries. So under these circumstances, you see the Pitchfork acting as if it would be a generic bifurcation.
What I claim is we forget about the symmetry. The symmetry is too restrictive. And we make this condition instead, which mainly excludes a saddle node. See, it's much more robust than assuming a symmetry. This condition rejects the possibility of a saddle node. And if you don't have a saddle node in the area, then there's no need for a symmetry hypothesis. And the symmetry hypothesis is extremely special. In biology, you don't have any symmetry hypothesis at all. Okay, so let me give a motivational setting for this. Okay, so in this first paper, I think when I spoke at IMPA last is before we had this. I don't remember when I was here, what I spoke about, but I believe this I did not talk about because we didn't have it at the time. And so what is in this first paper, Math of the Genome, sometimes we call it the dynamics of the genome. We construct a dynamical system, autonomous system of the form x prime equals f of x, where these high dimensional, well, there are 20,000 coding genes, for example, so this could have 20,000 variables in biology. And this f would be the expression level, the ith component would be the expression level of the ith gene. So what we did was to construct from the biology this dynamical system. That's in the first paper, which is already has been accepted online. You can read it. Okay, and that uses a network in the sense of a graphic. So we have a graphical structure defined by transcription factors and their targets in the genome. So these x's are going to be this form, x equals x1, xn, where the I here is a protein, as the gene. And the xi is going to be the level of activity of that gene. It's the level of expression. Could be interpreted as the amount of proteins percentage-wise. This goes back 100 years, these equations. Maybe 50, maybe 100. So these are the variables, the gene expressions, or the amount of protein corresponding to that gene. It's real numbers, positive, non-negative even. So we have just an ordinary dynamical system here in the sense that we all know. You write it down quite explicitly in terms of equations. Well, equations going back 100 years to Hill, well known in physics and chemistry. For us, see, we get this kind of picture. So these edges have the meaning that this transcription factor binds to the promoter of this gene. So this means this gene affects the level of transcription of this gene. You put all that together and you get a neat picture, pretty neat, idealized somewhat, and that's our basis for the dynamics of the genome. And it's all spelled out pretty carefully in the paper that's already published in FOCM Journal online. So you can find all that pretty well. This formal mathematical system described by transcription levels, transcription factors, and their targets, where they bind. And that's where we start doing Pitchfork. And we do that because of the following. So we have here this genome dynamics. Okay, this you could interpret as, for example, in a single cell, this could be the dynamics already taking place in that cell, even to some extent in the nucleus. Okay, so the idea is, here is a basin of that dynamics in a single cell. And we hypothesize, in fact, biologists to some extent also, that it approaches some kind of stable phenomena. It could, like circadian rhythm, introduce periodic solutions, but stable periodic solutions. Or it could be stable equilibria. So we for the moment, put aside the periodic solutions, stable periodic solutions, and that would be corresponding to a circadian rhythm, and eventually maybe the cell cycle. Okay, but I think not the cell cycle, actually. But we can, if we exclude those stable periodic solutions, we can identify a cell with a stable equilibrium. It may be, it will in general be very nonlinear, so it's like this. It's not linear. Previously, I think everybody who did this kind of mathematics assumed linearity of the genome dynamics. But then you lose a lot because then talking about stability of the equilibria doesn't make such easy sense. Okay, so we can focus now on the equilibria in that dynamics, the stable equilibria. Okay? Then we can identify a cell with the state at this equilibria. The state at this equilibria, we could think of interpreting these xi as protein levels. So we can look at the equilibrium distribution of the protein levels. That would be equilibrium of the xi's as defining a cell type. So a cell type then will be identified with this protein distribution at the equilibrium of that cell. The cells correspond then to their corresponding stable equilibria. Okay, so that protein distribution of the cell, equilibrium distribution, characterizes very much the function of the cell, because proteins define functions, so to speak. Proteins are the things that give function. Okay, so what this does is to allow the function of the cell be identified with the protein equilibrium distribution at the basin. Okay, so that was going to be part of my talk, and I'll just say a few words about that. So what one can do is to write these famous equations of Turing on morphogenesis. Turing's equations were linear, so he doesn't have the dynamics of the single cell or the genome expressed so well, but still very influential and a very good paper. So we use that as a starting point to look at this problem. How does one get the body to function? We have these different organs, tissues, what we call them. Tissues are like the liver, or tissues in the eye, tissues for muscle. These are the tissues for which the body functions. And they will depend primarily on proteins. But to get those good solid theory or solidify any theory, one would like to see how the proteins come together at this equilibria. But now in an organ like the liver, we have many, many cells. So we want to get the cells working together, coordinated action of the cells. So we want to expect the protein distributions at equilibria in a tissue like the liver or heart, or any tissue of so localized thing which is often an organ of the body. How do we synchronize that? And so what one does is to take a tissue here. Now we're going to write a tissue in terms of a different network. So here we have these are now cells in the tissue. Cells of the same cell type. So a tissue, sometimes biologists say this, and a single tissue is defined by cells of the same cell type. So for us, that would be cells which have the same equilibrium distribution of proteins. So what we want to do is to combine the genome dynamics. The genome dynamics works in each cell separately, and now we have some kind of diffusion, some kind of Turing-type diffusion between the cells in this organ, if you want, in the tissue. So what we do is to find conditions under which we have convergence to a common equilibrium distribution, taking into account the diffusion and the dynamics in each cell. It's a little subtle. What Turing proved in the linear case, in which we see very much, is a following problem. Turing said if you take a cell which is stable, he used linear stability, two cells, and if you put in diffusion, it's no longer stable. The famous example of Turing. So if you take two cells which are both stable, diffusion, then it becomes unstable. This is Turing's example. And I did the same thing about 40 years ago, where I said if you took two cells with a Turing model made nonlinear, you could take two stable cells and get a periodic solution. Two cells which were dead would come alive, because a periodic solution, stable, is like a heartbeat. So that was what I did a long time ago. So in this situation, then we followed this development, my early paper and Turing's paper, to obtain this theorem about emergence of a function. Emergence meaning that all the cells will have the same cell type with diffusion will converge, and we need a hypothesis which explains Turing's example too. We need a monotonicity hypothesis. So we have to assume monotonicity. Okay, so let's just use a linear example. And this, I'll give an example of dynamics which is not monotone. So it's going to be a spiral equilibrium, like this. This is not monotone because at some stage in the dynamics, you're getting farther away from the equilibria, even though it's stable. Everything is converging to this equilibrium, but at some points are getting away from, moving away. So we make a hypothesis, which can be done just in terms of some linear algebra and a inner product to prevent that. But this hypothesis, we found, lies behind Turing's example. His example, you had this monotonicity failing, and that leads to a general failure of eventually emergence. And so it led Turing to this problem of reaction diffusion equations, which would be where he found morphogenesis. So a lack of emergence is some kind of sign of morphogenesis. And it seems to us now that a key property there is failure of monotonicity. This is not monotone. This is a situation in Turing's example where you go away, and the idea is if you're, even though everything is stable separately, if you have two cells like this, but when it's going away, the diffusion can add them together to get something which destroys the stability. So it's diffusion which takes advantage of the fact you're getting farther away momentarily just to destroy the stable picture. So that's what we call monotonicity. Okay, well, in the last minute or two, let me just mention a motivation for all this, and this is the cell cycle. So we want to understand the cell cycle. It's a cycle when you have a cell dividing into two cells. And when a cell divides into two cells, there's two normal things that happens. They go in, one is into a different differentiated cell, a different cell type. Or it could be two cells of the same cell type. So cell cycle can just produce two cells which are like each other, symmetric division, two cells which are different from each other, asymmetric division. And for that, we use the Pitchfork bifurcation. Because the Pitchfork bifurcation, as I've said, corresponds to how the equilibria go from one stable to two stable. That would correspond, in our picture, to cell division in a cell cycle where you start off with one cell and you get two daughter cells, each with their own equilibria, their stable equilibria. And that's important to have a mathematical picture of that because that is a main cause of cancer when you have cell division which is not controlled. So abnormal cell division mutations is the main cause, maybe the main cause of cancer in its various forms. So that's why we're spending a lot of time right now on the mathematics of the cell cycle. And it's a little complicated for us in dynamical systems because what you're doing is you're changing the space. You're changing the number of cells. So one has to be very careful as you go around the cell cycle to monitor what all this means in terms of mathematics. Thanks very much.